Okay, we've got one more section in chapter 8, and we're still looking at hypothesis testing. We're just getting into a little bit more of the details and what we call mistakes when we do a hypothesis test, which can come up once in a while. So it says revisiting small p-values. A small p-value indicates to us that our test statistic is extreme, right? So remember that your p-value is always part of area that's shaded in the tails. So if you've got a small p-value, that means that you're farther into the tails, which means that's why you've got a small p-value, because you're farther into the tails. And so remember your test statistic, that's that z-score, right? So your test statistic would be, I like to say extreme. Sometimes they'll in the assignment they'll say large, or they'll use the term large for a test statistic. I would rather say extreme. I feel like that kind of emphasizes what we're talking about a little bit more. You're into the extremities of the graph. An extreme test statistic means something unusual, and therefore unexpected has happened. Unexpected has happened. So when we say unexpected, that means it didn't happen according to what we thought would happen with the population proportion. If we flipped a coin 30 times and we expected to get 15 heads, but we ended up getting 28 heads, then that's really unusual or unexpected, and that's what we're talking about. That means the sample that you got is not what you expected to get from the population. Let's write that down. The sample you got was not expected based on the population. That's what we're saying. Okay, so when you have an extreme test statistic, your sample is something that you did not expect. A small p-value leads us in that case then to reject the null hypothesis. This means that we have evidence in support of the alternative hypothesis. If the conditions concerning the sampling distribution of the z-statistic fail to be met, then we cannot find a p-value using a normal curve. So remember those three conditions that we talked about. The central limit theorem still has to apply, and that's why it's important for those conditions to be met. Sometimes that can happen if the samples are not randomly selected or if the sample size is too small. Those are usually the two situations where that could be an issue. There are two potential mistakes that could happen when you conclude a hypothesis test. So the first is what we call a type 1 error. So a type 1 error is when we reject the null hypothesis when it is actually true. So this is bad, this is not what we want. If we reject the null hypothesis but it's actually true, that's called a type 1 error. If we fail to reject the null hypothesis when the null hypothesis is true, that's good. That's what we would want, right? So if we don't reject the null hypothesis, that means we think the null hypothesis is true and the null hypothesis is actually true, that's a good thing. That's what we want. On the other hand, if we fail to reject the null hypothesis when the null hypothesis is actually false, that's a bad thing as well, and that we call a type 2 error. So when we make a type 2 error, what that means is we didn't reject the null hypothesis when we actually should have because it was false. On the other hand, if we do reject the null hypothesis and it's false, that's a good thing. That means we've concluded correctly what's actually happening in the population. So suppose a Flagler College student is working on his project and is interested in predicting whether the majority of Flagler College students support co-ed dorms on campus at a significance level of 5%. So the null hypothesis, remember we said when it's a majority test, just let your null hypothesis be that p equals 50%. Alternative then, since it's majority, would be that p is greater than 50%. So one error the student could make would be to reject the null hypothesis when it is actually true. So if he rejects the null hypothesis when it is actually true, that's a bad thing. This means concluding that if he rejects the null hypothesis, that means he thinks the alternative is true. So that means concluding that more than 50% of all Flagler College students support co-ed dorms when the actual proportion of Flagler College students who support co-ed dorms is 50% or potentially less. But that's what we're saying. He rejects the null hypothesis when it is actually true. So this would be an example of which type of error. If he rejects the null hypothesis when it is in fact true, that is a type 1 error. So let's add that. That means he has made a type 1 error. On the other hand, the student could fail to reject the null hypothesis when it is actually false. So he doesn't reject it, but it's actually false. This means that he thinks the null hypothesis is true. If he doesn't reject the null hypothesis, that means he thinks the null is actually true. So this means concluding that 50% or possibly less of all Flagler College students support co-ed dorms when the actual proportion of students who support co-ed dorms is more than 50%. So if he fails to reject the null hypothesis, let me say this again. I think I might have said this wrong. When he fails to reject the null hypothesis when it is false. Okay, so he fails to reject the null hypothesis. That means he thinks the null hypothesis is true when it's actually false. So if the null hypothesis is false, that means more than 50% actually support co-ed dorms. And so in that case, if he fails to reject the null hypothesis when it is actually false, that means he has made a type 2 error. So let's jot that down. That's called a type 2 error. The significance level of 5%, remember we had a 5% significance level right here. The significance level of 5% means that there is only a 5% chance. So the significance level, we haven't really gotten into this yet, but the significance level refers to the probability of making a type 1 error. So it means there's only a 5% chance that the student mistakenly concludes, see if he makes a type 1 error, he mistakenly concludes that more than 50%, so this is, let's see, there's 5% chance that the student, I want to add here that the student makes a type 1 error. So the significance level is the probability of making this type 1 error. So when the student mistakenly concludes that more than 50% of all Flagler College students support co-ed dorms, when in fact they do not, that means he's made a type 1 error. And so the 5% chance, the significance level or the alpha level, is the chance of making that type 1 error. The only way to reduce the probability of making of both types of mistakes is to increase the sample size. It would be a nice world if we could make the significance level arbitrarily small, but that doesn't really work. In the real world, if you're doing research, there's usually standards set for what these significance levels to be, or should be. The 5% is most common in social sciences, psychology, sociology, criminal justice, political science, education. When you read studies in those fields, 5% is sort of the gold standard that they use as the acceptable level of possible mistakes for those fields. And so the significance level is generally set. It's usually preset for the field. So unfortunately, we can't just arbitrarily make the significance level small. That's not really an option. The only way to reduce the probability is to increase sample size. Increasing sample size improves the, let's say, the precision of the test so that we make mistakes less often. Also remember what increasing sample size does. It reduces the standard error. Remember, larger sample sizes always mean smaller standard error. So anytime we can do that, we've reduced the probability of making one of these mistakes. Practical significance versus statistical significance. A result is statistically significant when we, let's see, I'm trying to think what I'm looking for here. When we reject the null hypothesis. The difference between the data estimated parameter value for a parameter and the null hypothesis value for the parameter is so large that it cannot be explained by chance. So whenever we make this conclusion where we reject the null hypothesis, we have something that is statistically significant. That means that the results we got from our sample are statistically significantly different from what we would have expected to get. However, statistically significant findings do not necessarily mean the results are practical. So here's an example of what I'm talking about. Suppose the proportion of people who get a certain type of cancer is 1 in 10 million. So first of all, if the probability of getting this cancer is 1 in 10 million, this is probably not something you're going to lose sleep over. This is not something you're going to worry about getting. It's a pretty rare cancer, 1 in 10 million. A statistical analysis shows that talking on a cell phone daily doubles the risk of getting cancer. So this means that the risk of getting cancer is now 1 in 5 million, right? Or 2 in 10 million, whichever way you want to say it. So 1 in 5 million. would this, practically speaking, cause a person to stop talking on a cell phone? So if the cancer risk is only 1 in 5 million, or I guess is more now, it's 1 in 5 million instead of 1 in 10 million, is that going to cause you, like I said, to lose any sleep over this? Probably not. Probably not. The chance is still very small. So we might have done some research and said, okay, this is a statistically significant difference from 1 in 10 million, but it's not practically significant. And so that's what we mean, that just because we get something that's statistically significant, it's not always practically significant. Okay? Does the result change our behavior or change what we're going to do in the real world? No. So let me see, a blank result is both statistically significant and meaningful. Honestly, I don't have my notes in front of me. I'm not sure what word I was looking for here. A significant, let's just say significant result. A significant result is both statistically significant and meaningful. Something that we would care about, in other words, should be both statistically significant and meaningful. Let's look at another example that's important that comes to how the phrasing and the words we use when we describe these. It says, a magazine advertisement claims that wearing a magnetized bracelet will reduce arthritis pain in those who suffer from arthritis. A medical researcher tests this claim with 233 arthritis sufferers randomly assigned either to wear a magnetized bracelet or to wear a placebo. The researcher records the proportion of each group who report relief from arthritis pain after 6 weeks. After analyzing the data, he fails to reject the null hypothesis. So be careful with that phrasing. He fails to reject the null hypothesis. Which of the following are valid interpretations of his finding? The magnetized bracelets are not effective at reducing pain. So that's a pretty definitive statement. They're not effective. There is insufficient evidence that the magnetized bracelets are effective. That's a little bit better. The magnetized bracelets had exactly the same effect. That's a pretty definitive statement as well. Or there was no statistically significant differences between the magnetized bracelets and the placebos at reducing pain. So what I want to point out about these phrases is you want to avoid anything that is super conclusive. Remember, I've always said statisticians always have to have an out, right? So we never want to be 100% sure about anything. There are always fluctuations. There's always things that could sway. So we don't want to say that the magnetized bracelets are not effective. They could be effective, and they could be effective for some people. So we don't want to say that they're not effective. We could say that there is insufficient evidence. Based on this study of 233 people, there is not enough evidence to conclude that they are effective. So I would say that's a good conclusion there. You can say that. There's not enough evidence to conclude that the bracelets are effective. The magnetized bracelets had exactly the same effect. Well, no, the two groups could have had slightly different values. The people who were effective and who had reduced pain in both groups were probably slightly different. So I don't think we can say exactly the same. That's pretty definitive as well. But we could say that there was no statistically significant differences. There might have been a difference, but it might not have been statistically significant, meaning that's where the information from the test comes from. So I would say both B and D are okay. So when you're phrasing your conclusions, these are the kind of words you want to say. There is a statistically significant difference, or there is no statistically significant difference, or there is insufficient evidence, or there is sufficient evidence. But we don't want to be definitive about one conclusion or the other. So here we go. Because we can never be 100% certain about our conclusions, avoid using phrases like, let me see, exactly the same, or completely different, or something like that. You never want to say that the null or alternative hypothesis is true. That's actually, a lot of students want to say that it's true. We don't want to say it's true. We want to say we have evidence to support one or the other. Maybe you could say we think this is true, or in your mind you could say we think this is true, but you never want to write the alternative hypothesis is true, or vice versa, false. You never want to say one is true or one is false. We always want to say we have evidence in support of the other. So we could say we have evidence to support whatever our conclusion is, okay? There is a statistically significant difference between the two groups. So there is or is not a statistically significant difference between the two groups. But you always want to be very careful with your phrasing for these. All right, let's look at confidence intervals and hypothesis testing. So very closely related are confidence intervals and hypothesis testing. So I remember I mentioned this the other day, that they go hand in hand. They really do complement each other. But the questions that one asks versus the other are slightly different. So for a confidence interval, the question might be something like this: what proportion of the population feels a certain way about a survey question? In your projects, this is what I had you guys do a couple weeks ago. You came up with a research question based on your survey, and the question you came up with was, what proportion of all Flagler College students feel blah, 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 whatever question you decided to use. To answer that, you're going to create a confidence interval. And that's going to give us a bound of what we think is true or what we think is the actual population proportion. Hypothesis test is more of a yes or no question. A hypothesis test is more something along the lines of, is the proportion of the population who feels a certain way different from something previous or something else? So you're comparing. With a hypothesis test, you're comparing. Is the proportion of the population who supports a certain candidate the same as 60%, or is it something different? We don't know with a hypothesis test what the proportion is. We just are comparing it to what we previously thought it was. So a hypothesis test is always going to be a yes or no question, essentially. So they're designed to answer different questions, but they lead us to similar conclusions. Confidence interval can lead us to the same type of conclusion as a two-sided hypothesis test.